Relativity, The Special and General Theory, by Albert Einstein, Appendix 3. The experimental confirmation of the general theory of relativity. From a systematic theoretical point of view, we may imagine the process of evolution of an empirical science to be a continuous process of induction. Theories are evolved and are expressed in short compass as statements of a large number of individual observations in the form of empirical laws, from which the general laws can be ascertained by comparison. Regarded in this way, the development of a science bears some resemblance to the compilation of a classified catalog. It is, as it were, a purely empirical enterprise. But this point of view by no means embraces the whole of the actual process, for it slurs over the important part played by intuition and deductive thought in the development of an exact science. As soon as a science has emerged from its initial stages, theoretical advances are no longer achieved merely by a process of arrangement. Guided by empirical data, the investigator rather develops a system of thought which, in general, is built up logically from a small number of fundamental assumptions, the so-called axioms. We call such a system of thought a theory. The theory finds the justification for its existence in the fact that it correlates a large number of single observations, and it is just here that the truth of the theory lies. Corresponding to the same complex of empirical data, there may be several theories, which differ from one another to a considerable extent. But as regards the deduction from the theories which are capable of being tested, the agreement between the theories may be so complete that it becomes difficult to find such deductions in which the two theories differ from each other. As an example, a case of general interest is available in the province of biology, in the Darwinian theory of the development of species by selection in the struggle for existence, and in the theory of development which is based on the hypothesis of the hereditary transmission of acquired characters. We have another instance of far-reaching agreement between the deductions from two theories in Newtonian mechanics on the one hand, and the general theory of relativity on the other. This agreement goes so far that up to the present we have been able to find only a few deductions from the general theory of relativity which are capable of investigation, and to which the physics of pre-relativity days does not also lead. And this despite the profound difference in the fundamental assumption of the two theories. In what follows, we shall again consider these important deductions, and we shall also discuss the empirical evidence appertaining to them which has hitherto been obtained. A. Motion of the perihelion of Mercury. According to Newtonian mechanics and Newton's law of gravitation, a planet which is revolving round the sun would describe an ellipse round the latter, or more correctly, round the common center of gravity of the sun and the planet. In such a system, the sun, or the common center of gravity, lies in one of the foci of the orbital ellipse in such a manner that, in the course of a planet year, the distant sun-planet grows from a minimum to a maximum, and then decreases again to a minimum. If instead of Newton's law we insert a somewhat different law of attraction into the calculation, we find that, according to this new law, the motion would still take place in such a manner that the distant sun-planet exhibits periodic variations, but in this case the angle described by the line joining sun and planet during such a period (from perihelion closest proximity to the sun to perihelion) would differ from 360 degrees. The line of the orbit would not then be a closed one, but in the course of time it would fill up an annular part of the orbital plane, that is, between the circle of least and the circle of greatest distance of the planet from the sun. According also to the general theory of relativity, which differs of course from the theory of Newton, a small variation from the Newton-Kepler motion of a planet in its orbit should take place, and in such a way that the angle described by the radius sun-planet between one perihelion and the next should exceed that corresponding to one complete revolution by an amount given by the formula plus 24 pi cubed a squared divided by t squared c squared times the quantity 1 minus e squared. NB. One complete revolution corresponds to the angle 2 to the pi power in the absolute angular measure customary in physics, and the above expression gives the amount by which the radius sun-planet exceeds this angle during the interval between one perihelion and the next. In this expression, A represents the major semi-axis of the ellipse, E its eccentricity, C the velocity of light, and T the period of revolution of the planet. Our result may also be stated as follows. According to the general theory of relativity, the major axis of the ellipse rotates round the Sun in the same sense as the orbital motion of the planet. Theory requires that this rotation should amount to 43 seconds of arc per century for the planet Mercury, but for the other planets of our solar system, its magnitude should be so small that it would necessarily escape detection. Footnote. Especially since the next planet Venus has an orbit that is almost an exact circle, which makes it more difficult to locate the perihelion with precision. End footnote. In point of fact, astronomers have found that the theory of Newton does not suffice to calculate the observed motion of Mercury with an exactness corresponding to that of the delicacy of observation attainable at the present time. After taking account of all the disturbing influences exerted on Mercury by the remaining planets, it was found (Leverrier 1859 and Newcomb 1895) that an unexplained perihelial movement of the orbit of Mercury remained over, the amount of which does not differ sensibly from the above-mentioned plus 43 seconds of arc per century. The uncertainty of the empirical results amounts to a few seconds only. B. Deflection of light by a gravitational field. In section 22, it has been already mentioned that, according to the general theory of relativity, a ray of light will experience a curvature of its path when passing through a gravitational field, this curvature being similar to that experienced by the path of a body which is projected through a gravitational field. As a result of this theory, we should expect that a ray of light which is passing close to a heavenly body would be deviated towards the latter. For a ray of light which passes the Sun at a distance of delta sun radii from its center, the angle of deflection (alpha) should amount to alpha equals 1.7 seconds of arc divided by delta. It may be added that, according to the theory, half of this deflection is produced by the Newtonian field of attraction of the Sun, and the other half by the geometrical modification (curvature) of space caused by the Sun. This result admits of an experimental test by means of the photographic registration of stars during a total eclipse of the Sun. The only reason why we must wait for a total eclipse is because at every other time the atmosphere is so strongly illuminated by the light from the Sun that the stars situated near the Sun's disk are invisible. The predicted effect can be seen clearly from the accompanying diagram. Reader's annotation. Figure 5. The Earth is shown as a dot at the bottom of the diagram. A straight line proceeding from there, labeled D sub 1, proceeds upward and slightly to the right, passing the Sun at a tangent, Sun being represented by a circle. A second line, labeled D sub 2, starts at the Earth, proceeds at a relatively smaller angle, which results in its passing the Sun at a greater distance than the initial line D1, which is signified by the symbol delta. After passing the Sun, the line becomes parallel to D sub 1. End of reader's annotation. If the Sun (S) were not present, A star which is practically infinitely distant would be seen in the direction d sub 1, as observed from the Earth. But as a consequence of the deflection of light from the star by the Sun, the star will be seen in the direction d sub 2, that is, at a somewhat greater distance from the center of the Sun than corresponds to its real position. In practice, the question is tested in the following way. The stars in the neighborhood of the Sun are photographed during a solar eclipse. In addition, a second photograph of the same stars is taken when the Sun is situated at another position in the sky, that is, a few months earlier or later. As compared with the standard photograph, the positions of the stars on the eclipse photograph ought to appear displaced radially outwards (away from the center of the Sun) by an amount corresponding to the angle A. We are indebted to the Royal Society and to Royal Astronomical Society for the investigation of this important deduction. Undaunted by the war and by difficulties of both a material and a psychological nature aroused by the war, these societies equipped 2 expeditions to Sobral, Brazil, and to the island of Principe, West Africa, and sent several of Britain's most celebrated astronomers, Eddington, Cottingham, Crommelin, Davidson, in order to obtain photographs of the solar eclipse of 29th May 1919. The relative discrepancies to be expected between the stellar photographs obtained during the eclipse and the comparison photographs amounted to a few hundredths of a millimeter only. Thus, great accuracy was necessary in making the adjustments required for taking of the photographs and in their subsequent measurement. The results of the measurements confirm the theory in a thoroughly satisfactory manner. The rectangular components of the observed and of the calculated deviation of the stars (in seconds of an arc) are set forth in the following table of results. Reader's annotation. The table consists of measurements on 7 stars, which are then tabulated in 4 additional columns, which are entitled first coordinate and second coordinate, and then for each of those, the observed and calculated measurements are given. End reader's annotation. Number of the star, 11. First coordinate, observed, minus 0.19, calculated, minus 0.22. Second coordinate, observed, plus 0.16, calculated, plus 0.02. Star numbered 5. First coordinate, observed, plus 0.29, calculated, plus 0.31. Second coordinate, observed, negative 0.46, calculated, minus 0.43. Star number 4, observed, 0.11, calculated, 0.10. Second coordinate, observed, 0.83, calculated, plus 0.74. Star number 3, observed, plus 0.20, calculated, plus 0.12. Second coordinate, observed, plus 1.00, calculated, plus 0.87. Star number 6, observed at the first coordinate, plus 0.10, calculated, plus 0.04. Second coordinate, observed, plus 0.57, calculated, plus 0.40. Number of the star, 10. Observed, minus 0.08, calculated, plus 0.09. Second coordinate, observed, plus 0.35, calculated, plus 0.32. Number of the star, 2. Observed, plus 0.95, calculated, plus 0.85, and at the second coordinate, observed, minus 0.27, calculated, minus 0.09. C. Displacement of the spectral line towards the red. In section 23, it has been shown that in a system K', which is in rotation with regard to a Galilean system K, clocks of identical construction, and which are considered at rest with respect to the rotating reference body, go at rates which are dependent on the position of the clocks. We shall now examine this dependence quantitatively. A clock, which is situated at a distance r from the center of the disk, has a velocity relative to k, which is given by v equals omega r, where omega represents the angular velocity of rotation of the disk k prime with respect to k. If v sub 0 represents the number of ticks of a clock per unit time, parentheses, quote, rate, end quote, of the clock, close parens, relative to k when the clock is at rest, then the, quote, rate, end quote, of the clock, parentheses, v, close parens, when it is moving relative to k with a velocity v, but at rest with respect to the disk, will, in accordance with section 12, be given by v equals v sub 0 times the square root of 1 minus v squared over c squared, or with sufficient accuracy by v equals v0 times the quantity 1 minus 1/2 v squared over c squared. This expression may be also stated in the following form: v equals v sub 0 times the quantity 1 minus 1 over c squared times omega squared r squared over 2. If we represent the difference of potential of the centrifugal force between the position of the clock and the center of the disk by phi, that is the work considered negatively which must be performed on the unit of mass against the centrifugal force in order to transport it from the position of the clock on the rotating disk to the center of the disk, then we have phi equals minus omega squared r squared divided by 2. From this it follows that v equals v sub 0 times the quantity 1 plus phi over c squared. In the first place, we see from this expression that the two clocks of identical construction will go at different rates when situated at different distances from the center of the disk. This result is also valid from the standpoint of an observer who is rotating with the disk. Now, as judged from the disk, the latter is in a gravitational field of potential phi, hence the result we have obtained will hold quite generally for gravitational fields. Furthermore, we can regard an atom which is emitting spectral lines as a clock, so that the following statement will hold. An atom absorbs or emits light of a frequency which is dependent on the potential of the gravitational field in which it is situated. The frequency of an atom situated on the surface of a heavenly body will be somewhat less than the frequency of an atom of the same element which is situated in free space, parentheses, or on the surface of a smaller celestial body, close parentheses, period. Now phi equals minus k times m over r, where k is Newton's constant of gravitation and m is the mass of the heavenly body. Thus, a displacement towards the red ought to take place for spectral lines produced at the surface of stars as compared with the spectral lines of the same element produced at the surface of the Earth. The amount of this displacement being v sub 0 minus v divided by v sub 0 equals k over c squared times m over r. For the Sun, the displacement towards the red predicted by theory amounts to about 2/millionths of the wavelength. A trustworthy calculation is not possible in the case of the stars, because in general neither the mass m nor the radius r is known. It is an open question whether or not this effect exists, and at the present time astronomers are working with great zeal towards the solution. Owing to the smallness of the effect in the case of the Sun, it is difficult to form an opinion as to its existence. Whereas Greb and Bachem, Bahn and Prenz, as a result of their own measurements and those of Evershed and Schwarzschild on the cyanogen bands, have placed the existence of the effect almost beyond doubt, other investigators, particularly St. John, have been led to the opposite opinion in consequence of their measurements. Mean displacements of lines towards the less refrangible end of the spectrum are certainly revealed by statistical investigation of the fixed stars, but up to the present the examination of the available data does not allow of any definite decision being arrived at as to whether or not these displacements are to be referred in reality to the effect of gravitation. The results of observation have been collected together and discussed in detail from the standpoint of the question which has been engaging our attention here in a paper by E. Freundlich entitled Zur profunder Allgemeinen Gravitationstheorie Die Naturwissenschaften 1919, number 35, page 520, Julia Springer, Berlin. At all events, a definite decision will be reached during the next few years. If the displacement of spectral lines towards the red by the gravitational potential does not exist, then the general theory of relativity will be untenable. On the other hand, if the cause of the displacement of spectral lines be definitely traced to the gravitational potential, then the study of this displacement will furnish us with important information as to the mass of the heavenly bodies. End of Appendix 3.